You I will just remind us of the importance of our correct vocabulary, of course. The ones I've highlighted, we knocked those out of the park yesterday or refreshed ourselves on them. So electrochemistry involves redox reactions. Redox reactions. And Abby, I need to put a new packet in your hands. And so that is just a listing of some terminology. Today, I want to show us the terms that we will add to our repertoire, if you will. You are welcome. So by the end of our time, we will also know galvanic, which is one and the same. It's frustrating when we can use multiple terms to mean the same thing. You most often will see the use of galvanic and voltaic cell interchangeably, but we can also call it a Daniel cell. So we'll get those. We will also talk about a half cell. We saw a voltmeter yesterday. We will also learn about a volt. We will also learn about an EMF, E of a cell. We will also learn reduction potential, anode, cathode, salt bridge. So that will just leave for us practice Monday, and then these last two and related terms. So a lot of great learning today. And I will especially encourage us to imagine things on the particle level. All right. So yesterday we got to see the creation of a battery, yes? And we talked about using an oxidation and a reduction half reaction to release and then absorb electrons. So we looked at this kind of core reaction saying, okay, we know that zinc is oxidizing. So we have zinc solid producing zinc ion. So this is the oxidation half reaction. And if we would place the reactants and products together in a compartment, this, we called it a half reaction in unit 4, but it's called a half cell because it's half of the complete battery kind of ingredients, if you will. All right, but we don't have oxidation without reduction. And so our reduction was the copper ion accepting those two electrons to form elemental copper. And as long as we have copper ion, the product, then this would have been the other half cell that together make up the voltaic cell. Okay, well, we needed to put these into contact, and we should have a site for electrons to be given to or taken from. So just like, have you ever made rock candy? Do we even know what that is? Okay, you've consumed, oh, yeah. So how did you make rock candy?
So I dissolved a lot of sugar in a cup of water, and then of course I had to put food coloring in it. Yeah. And then I started a
Pipe cleaner, a string, a lollipop stick.
yeah, inside the cup.
So you made a super saturated sugar solution. I bet you had to heat up the water to get, like, it's a crazy amount of sugar that will dissolve. Sugar has a very high solubility. And then you suspended, I bet, like a lollipop stick or whatever. Well, crystallization will happen on that stick. It's a solid surface for solid to collect upon. Now, whenever you make rock candy, though, other obstacles can get in your way. for example, if there's scratches or something on, or I've done it in a styrofoam cup, it has a very irregular, bumpy surface, and you'll get crystal growth inside your cup, but you of course want it on the stick for you to enjoy, as Teddy said he has at some point in time. But the thing is, how does this relate to a battery? That's what these solid surfaces do. In the case of a battery, we call them electrodes. And then we connected the voltmeter, but it was not successful until the salt bridge. All right, so what actually was a successful battery? And so why don't I'm going to draw it here. So we understand that in one of the beakers, and Luke, you choose. In this beaker, do I want it to be my copper or the zinc? You choose. All right. So I had a solution that provided the zinc ion, and then I had a solid piece of zinc. And then in this, I had a source of the copper ion and then a piece of solid copper. And I understand that I need to put them in contact so that the copper ion will end up pulling electrons to form elemental copper. So this is my reduction. And then the zinc gave the ions by releasing the electrons. And so this is my oxidation. Okay, but how did the electrons get from here to there? We need to put them into contact. And that's what we did, of course, with the voltmeter. But ideally, what we'd want to do is put a light bulb in that path, put a cell phone, something that when the electrons are moving, so we need electrons are leaving, going over here, that we can get work out of it. So if we put a light bulb, or if we put a voltmeter, it will just tell us the push or pull on the electrons. But when I connected it, no voltage was read because we need a salt bridge. So remember, kind of lamely, I took paper towel, soaked it in the sodium chloride, and then made sure that the ends were in contact. So I could have made it a little bit more, I don't know, fancy. If we take a glass tube and then put 2 L bends in it and then stuff it with cotton and then soak that in the sodium chloride solution, then the cotton, of course, and the sodium chloride solution would move through the cotton, and then I could just lower it in instead of having, just paper towel. But this acted as the salt bridge. All right. This is a voltaic cell. Go ahead, sir.
Wouldn't the zinc also want zinc ions also want 2 electrons? The oxidation side, but mostly.
Can we get back to your question probably in 3 minutes? That's an excellent question. That's an excellent question. Can we pause on that? Okay. Now, some other terminology. The half reaction where the reduction is happening is called the cathode. The cathode. So wherever, this whole compartment is called the cathode. Where the oxidation is happening, we call the anode. And here is an excellent way to remember. Thou, consonant, consonant. So the reduction occurs at the cathode, the oxidation at the anode. In a voltaic cell, electrons will always flow from the anode to the cathode. Okay, in a voltaic cell, electrons flow from the anode to the cathode. Okay, now what makes it a voltaic cell? It is thermodynamically favored. As long as we have our ingredients and have everything connected properly, we just connect everything and it goes, right? You purchase a battery when your calculator needs battery power, you put your batteries in, press the button, it's on. It just does its job. So that's what makes it a voltaic or galvanic or Daniel cell. Those are used interchangeably. Thermodynamically favors, which will do electrical work for us. Okay. Now, why the salt bridge? Can we imagine the particle level? Can we imagine the particle level? And so we need to get on that Miss Frizzle, school bus and go in to this half cell, our anode. So what we are saying is, this is our oxidation. The zinc solid is forming zinc +2, giving 2 electrons. So as the reaction is going, solid is becoming a soluble ion. So we are losing zinc solid and we are gaining zinc ion. And then the opposite here. Here in the cathode, we are saying the copper is accepting the electrons that are coming in, and it is forming more copper. We're losing the copper ion, forming more copper solid. Yeah. In fact, remember, I showed us these. This has been sitting since yesterday. Now, this, of course, was the zinc in direct contact with the copper solution. But the copper solution would begin beautiful blue, and look at it today. The copper +2, so it would begin blue, but then we would see an increase in the copper electrode with copper depositing itself, and then we'd eventually become colorless. Batteries die, don't they? Well, why? Because you run out of what is moving or pulling for the electrons. Okay, but why the salt bridge? As this reaction is happening, this is becoming more and more positive. As this reaction, we're losing positive. So this will become negative because we know there's spectators that have to be in there. Nature doesn't allow that to happen. Remember, we've said since the beginning of the earth, there's no such thing as like a bottle of cation or a bottle of anion. Nature just, it's going to become neutral. So the electrons will stop moving unless we can provide an ingredient that will keep the charge balanced. That's what the salt bridge does. That's what the salt bridge. Okay, so we know salts, soluble, are cations and anions. We just need to make sure we are choosing a salt that won't react with anything in the anode or cathode. So let's choose like our go-to spectators. They're saving the day again. How about sodium ion? How about nitrate ion? Okay, so Zach, in the anode, as this reaction is happening, we're getting more and more and more positive. So we're gonna have a salt bridge that's made of sodium ion and nitrate ion. To maintain electrical neutrality, what will flow into this anode to prevent us from, yeah. So the anion, in this case, will flow in that direction. So as we form one zinc +2, 2 nitrates will come in. As we form another one, another 2 will come in. Also, some zinc ion could kind of, but usually this is big enough, just as long as the electrical neutrality is balanced. And here, as we are becoming more negative, well, then the sodium ion will flow in here. So the cation will flow in that direction. So that's the reason for the salt bridge. Okay. All right. I have a great animation. If you could just enjoy this. So we can definitely tell, it's ooh. A little different of a setup than, of course, I did. So look at this fancy dancy salt bridge. So I bet it's just filter paper that is saturated in the salt solution. And then we have the copper with the copper ion. You can see the light blue, and then zinc and so on. So they're referencing what we just, but what I love is
to the atomic scale and see how this cell operates.
particular diagram.
Here at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution.
What are the yellow flashes? Ha! Why would they be flashing? 18 students, excellent. Yeah, so we know, just zinc being zinc, that this will be a sea of electrons. Okay, excellent job, excellent. These are the nitrates that are helping, that are the spectators. All right.
Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper 2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper 2 ions leave the solution and are reduced at the cathode.
Okay, concerns? I
think we should explore a few solutions.
Love the accuracy of that video. Did anyone observe the formation of cation when neutral zinc forms zinc plus 2, it decreased in size. And then when the copper plus 2 became neutral copper, it increased in size. So remember, electrons in and of themselves really don't have any appreciable volume, but can add or create electron-electron repulsion. So when we lose them, the remaining electrons can get a little closer. That's why cations are smaller. And then when they're added, they cause a bunch of repulsion. So the electron cloud has to increase in volume. So a reminder of that. All right, can we then go back to what we were just taking a look at to answer Zach's question? So I'm sorry, sir, we're more than 3 minutes later. Okay, so what Zach was saying is, well, why doesn't zinc take the electrons? All right. Are we ready to turn? I know we are, the big four. Okay. This, a standard reduction potential. What are we talking about? All right. So here's a listing of all reduction half reactions. Now, why is it called a half reaction? Because we know it's not complete unless we have an oxidation. But these are all reductions. Okay, what is this E naught thing? All right, if we turn over cell potential, when we have a voltaic cell, so this is a simplified drawing. They're calling it Daniel cell. Remember, that can be another term for it. Well, we need to have some way to report, well, how much electrical work can this do? That is the cell potential. Okay, cell potential. Now you'll see, usually just the printed capital E, usually that's energy. So we try to make a little bit different. It's like a fancy curly E. My patheticness, I usually just make it like that, kind of an E. But we also have to understand it could just be a capital E. Okay, but we use an E to represent it. And if we're talking about the entire cell, then we'll give it the little subscript of cell. So for example, a AAA battery, a AA battery, it has an electromotive force or a cell potential of 1.5 volts. All right. The cell potential is the driving force on the electrons. It is a measure of the strength of the pull that a reducer has, God bless you, or the push that an oxidizer has. So it's up to you, whichever way you want to think of it. Okay, so my coffee maker. I always keep my coffee maker plugged in. And we know American outlets, they have a potential of 120 volts that they can provide. So man, there are electrons there waiting because copper wiring is connected to, et cetera, et cetera. Okay, they're there. But they don't come to then power until I press the brew button. So what does, pressing start on your microwave, depressing down on your toaster, what does that do? Pressing on your calculator. So if we want to think, that causes a downhill for the electrons to flow, or a potential. So the question is, how much of a downhill is there? So we know the steeper it is, then we could say the more likely the electrons will flow. A measure of that is voltage, if that's okay. Okay, so the steeper the hill, the greater the voltage value. And we call that potential. Okay, a volt is defined as a joule per coulomb. And that's always kind of like, what?
So confusing if you go into units. Like 13 different ways to.
Yeah, I know. I know. And so I like to just know, okay, what can happen with 1.5 volts? What can that do for me? What a 9-volt battery, what can that do? That's usually what I just try to numerically, and I don't know. Yeah. All right. So if it is a positive voltage, that is thermodynamically favored. If it is negative, it is not thermodynamically favored. So let us apply amazing students our understanding of atomic structure. Look what has the greatest positive voltage assigned to its reduction. Fluorine becoming fluoride. That should make total sense, knowing the electronegativity, which is revealed through, right, the atomic structure. So we know, man, fluorine has a really strong pull for electrons and then has its octet satisfied, but it's really, you know, the pull the electron, the nucleus has, because we're just adding to the second energy level, and the amount of energy that Coulomb's law could reveal for us, so all that good stuff. And then if we look at kind of the bottom, these, don't want to be reduced, quote unquote, not that they want, but really are not thermodynamically favored. Well, aren't these some of our most reactive metals, that they're so reactive because they're forming the lithium ion? And so it wouldn't be thermodynamically favored to reverse it. Huh? Okay. If we find what is zero, just like we assign electronegativity values and we say fluorine, the most electronegative, based upon experimental measurements, we're going to say it has an electronegativity of 4. And everything else will be assigned a value in comparison. Or carbon is assigned an average atomic mass of 12.01, and then every other element is assigned based upon that, but it's based on experimental data. Well, we assign this reaction to have a voltage of 0. So the standard reduction potential of hydrogen, or the hydrogen reduction standard reaction. Okay, all right. So why doesn't zinc reduce where copper does? Well, let's take a look. All right, so I want to find the measure of copper reducing. That's a voltage of 0.34. Well, zinc, that's why. That is not thermodynamically favored. So when put into contact, you're like, the possibility is there. So the more positive the voltage, the more thermodynamically favored. All right, Teddy, you're going to slam dunk this. I'm sorry that this will probably insult your amazing intelligence. Let's go with calcium. Well, what if instead of having the calcium +2 ion reduce, what if we would have calcium oxidize? What would be the voltage for that? Because
It's the opposite of oxidizing. It's it oxidizing.
I know.
Leo the Lion sister. So our
No. Wait.
in charge. You know what? I'm gonna stop talking now.
You made, you made it or I don't know what we did. Okay, so the deal is, if this is non-thermodynamically favored in this direction by that much, so that means we have to put in that work to get this to happen. Well, if we reverse it, that is the amount that it will be thermodynamically favored. So anytime we reverse these, their signs are going to reverse. Okay, but they are intensive. They are intensive. These are volts, joule per coulomb. It is not joule per coulomb mole of reaction like our thermodynamic quantities. So remember, in thermodynamics, if we would flip a reaction, we would reverse the sign on enthalpy. And if we would need to multiply this through by 2, we would do the same to our thermodynamic quantity because it was per mole of reaction. This isn't per mole of reaction. So we will see the need to sometimes manipulate these coefficients. The only thing that ever changes about the EMF is the sign. Okay, so what would be the cell total potential for copper plus 2 for the battery that we made? So this 0.34 volts, and then the zinc was becoming zinc ion, and that will be 0.76 volts. When I add to get my overall reaction, just like we added prior, we can add these and we will get 1.40 volts, right? Oh my gosh, Mrs. Gerhardt, 1.10. Whew. Okay, but notice it's an E with the floating 0. So that means 25 Celsius, 1 ATM, but 1 molar solution. So the battery that I made for us measured greater than 1.10 volts because I had different concentrations of the ions. Okay. All right. So, oh, this table, it has a little bit of a larger selection of reduction reactions. What's on the back of this is what the College Board provides us. I provided this again at the very back because we'll be referencing this a lot. And I just thought, oh my gosh, I need to include it maybe in the back. It's just more handy for us to flip to the back. All right. So can we let's go to page 9. Page 9. Okay, so let's say that Sarah comes into class and says, Miss Gerhardt, I saw these reactions in our reduction table. Can we make a battery out of these? Okay, well, first I would say, oh, I'm sorry, Sarah, I did not include the complete products of this. So we have iron reducing, the iron plus 2 to make iron. I already provided us that value, but we need the rest, the products of this, which I know that Jackson is thinking, but Mrs. Gerhardt, didn't we in our reduction titration earlier in the year, remember that really, really dark purple solution? Wasn't that permanganate? Didn't we react it with the iron plus 2 ion and it made a colorless solution? I remember, this is all coming back, isn't it? That we'll make manganese plus 2. I'm just gonna, I'm not sure if this is on the, it's on the more extensive, sorry. I'm sorry. The 1.51. So it manganese plus 2 and then 4 waters. There we go. Okay. So Sarah's question is, can we make a battery out of this? All right. Now, if I can just foreshadow that many, many times, this is how we will start an electrochemistry problem. Don't have to grab it, this yellow packet. Do you see they could give us two reduction reactions and the potentials. We're given and so on, okay? So a lot of times, that's what we're starting with, two reductions. Okay, if we're gonna make a battery, for crying out loud, we want it to be thermodynamically favored and to provide as great a voltage as possible. You are given two reductions. We need to choose, okay, which one is going to be our oxidation? Which reaction do I flip so that when I add my half cell potentials, I get the largest positive value? All right, so what do I mean? Well, if I make these products the reactant, then this is going to be negative 1.51. And then, oh gosh, I'm just going to get a bigger negative number. Where if I would make this the oxidation, then I get a bigger positive when I add them together. All right, so I am going to equip my battery with solid iron, understanding that when I put everything connecting, this will be my oxidation. Oxidation happens at the anode. And the E naught of that will be positive 0.44 volts. Okay, and then the permanganate will need 5 electrons along with some acid, and I will be making manganese +2 and some water in that half cell, and that'll be 1.51 volts. Okay, if we want to just go ahead and say, because even if we need to manipulate this in any way, I know that I will just add these. Woo, not too shabby. Sarah, good selection of ingredients for this battery. I know it. Okay.
Like the battery.
I'm the queen, or whatever title you want. Wait, did you say the back?
Like mattress.
I know. I know. Okay. Whenever we if we see like the title of this page, it says complete description. Well, we need to get, okay, well, how many volts, and then what is the overall reaction for our battery, the overall reaction? Okay, the iron, every 1 mole of iron can provide 2 electrons, but every 1 mole of permanganate ion needs 5. So, lowest common multiple, we are going to need to multiply through by 5, multiply through by 2. But our voltages don't change. So that's why I could add that up now. So our balanced equation will be 5 Fe solid plus 2 MnO4 negative. And we know electrons will end up canceling out. Plus 16 hydrogen ion will yield 5 iron plus 2 manganese plus 2 plus 8 waters. Yeah. And I definitely want to give just a double checking, make sure I didn't forget anything. We also should check to make sure that charges are balanced. So I have 16 plus 1s and 2 minus. So on this side, it's going to be positive 14. I have plus 10. Oh, yay! Positive 14. Balanced. So balanced reaction. Okay, so what would be the physical setup? That's the drawing. All right. It is your call. It is your call. Where are you going to put the anode or the cathode? I just am in the habit, I usually put my anode on the left, but it's absolutely up to you. It does not matter. And we can't always expect the anode to be on the left. So should we draw it on the right just in case? Or it doesn't matter?
Do it on the left. Sorry, I already
Okay. All right. Well, we know we're gonna have a salt bridge required. And unless you know what your salt bridge is composed of, we don't have to identify the actual formula. We can just say salt bridge. And we know we're gonna have aqueous solution because we have ions. And we know we must have solid for the electrons to be given to or taken from. Okay, now we know water's there. So my anode is my oxidation. Sugar. All right, that's where we pick up Monday. Erg. Have a great, great weekend.